Welcome back, everyone, to this weekly podcast of the School of Logistics with Pauline and Michiel. Thank you for being here again.
Thank you.
So, last week we had the opportunity to go to an event about quantum computing. Michiel, you were there as well. What did you think of the event?
It was interesting, although I expected even more advanced information. Like I wanted to know what's the cutting edge, and it was a very broadening event, like inviting everyone to be involved. So also the basics were covered, which is good, but I wanted more actually.
That is funny because that is not the feedback I heard from other people in the audience.
Well, yeah, different expectations maybe. But I definitely learned a lot, especially the last presentation was about a randomness generator, which is actually something that's pretty hard to do. Like computers can generate like results, like specifically calculating, that's very easy for them to do. But asking them to say something random is very hard to do. And there was a guy who has a startup specifically with a device to generate quantum safe randomness.
You know, it's so funny that you mentioned that because I heard that that is your highlight from the events because someone I talked to, which was not you, Michiel, he actually mentioned that that was the part he disliked most because he was looking for like futuristic business applications. And then, then a randomness generator is not really something that inspires a lot of maybe business ideas.
It's more fundamental, but that's the stage that quantum is currently in. It's at the fundamental level. Like it's too early, I think, to really look at what can it mean for this vertical, what can it mean for logistics, what can it mean for that. That's just too early right now. It's not there yet. So the randomness, although you can say it's not really like what is quantum, and it was on the edge of what you can consider as a quantum technology. Because it kind of took a leap with what is quantum there, but it's an interesting application.
And why is randomness generation with a quantum? What does it mean that something is quantum proof in terms of a random number generator?
Yeah, that goes back to encryption standards, which we use now heavily, like public-private key encryption. If you want to send me something over the internet, and I want to know that A, it's coming from you, and I want B, I want no one else to be able to read it. And that's based on prime factorization. So when you have a given number, a very large number, but this number is made out of the multiplication of two prime numbers. So it can only be the product of those two prime numbers and cannot be split further anymore. Doing a multiplication is very easy, but going from the large number back is very hard. Unless you have a quantum computer, then it becomes easier to do. And then anybody could pretend to be you and sign things with your certificate, or you can hack whatever is now encrypted.
And do you see that as a threat, for example, for data that is stored today? Will it still be safe in 5 or 10 years?
That's already being done, like store now, decrypt later. So people gather data now because in, let's say, 20 years, there was a wild debate, of course, there, but let's say in 20 years, probably we will be able to decrypt some of the things that are encrypted now. So they just gather all the data, and it's like a declassifying moment, and which they had, like it was another T date or it was a Q date or something, like the date when everything becomes available.
Exactly. I think they called it Q Day or something.
Something like that.
The day that all the data will be available for everyone, but it's not there yet. But what if we go back to the basics? How would you see quantum computing in logistics, maybe in a really easy way? How does it help to do more in logistics, maybe?
Very difficult question, as it's very early for seeing the applications of the technology. What it's very good at is fuzzy logic or fuzzy calculation. So multiplications of multiple integers at scale. And if we say that, then of course we think about AI, and what AI is doing is it's not an exact calculation, it is a fuzzy calculation, it needs to be done at scale. So what I think is that it will make neural networks easier. So it will make the processing of neural networks faster. And so the applications will be for any industry, of course.
And if you say faster, right now there's also the debate whether AI takes up too much energy. Is it also energy efficient, but way faster, or is there a benefit to energy?
Depends on the technology. At the moment, it's very non-efficient, definitely, because you have to imagine that you have to have this qubit, and you want to control what it does. And our current way of controlling what this qubit does is making it very cold. So it needs to be near 0 Kelvin to actually control what it's doing. If it's not near 0 Kelvin, then it does too much things and you cannot control like the state of it. So currently, if you see like a picture of a quantum computer, I think 99% of it will be just the cooling, and then you have this tiny, tiny chip, which is actually the computer.
Yeah.
So is it very energy efficient? At the moment, definitely not. If you use it well, of course, then you can do in seconds what now takes billions of years. So yes, it's energy efficient in that sense.
Yeah, that's an interesting take. You talked about the qubit. How is that different from the normal standard n bit or just the regular bit that we know?
Yeah, so the regular bit, of course, is a 0 or a 1. And if you measure it in voltage, like you have 0 voltage or a low voltage or a high voltage, and a qubit can be anywhere in between. So it's like, I think we had the example of a light last session, where we had the light is on or off, but you can also have like a dimmable light. And you can think of a qubit as being something like that. It's a dimmable light. When you have 2 bits, you can multiply them. So 0 times 1 equals 0, of course, and you have these multiplications. But imagine if you have to do 0.5 times 0.8. It takes some more calculation to do this, actually. Whereas in a qubit world, you would have these 2 qubits who are something in between. You multiply them in the same speed as you would do with a normal bit, which of course is very efficient in a qubit world.
And that's something.
I feel like this is where you've lost us.
I heard the superposition is the term for that, because you don't know what state a qubit is in unless you have the solution. If I
That's the Schrödinger's cat example. Like when you have a cat in a box, and I think the original example is something with radiation. So the cat is either like already radiated and it's dead, or it's not dead. And it's that and not that until you look in the box. And that's a little bit the same thing with the qubit. It can be 0 or 1 until you look. And then it's not a superposition anymore, but then it's like what you see is what it is now. And you have to actually do the calculation multiple times, because it's a probability that it will be either 1 or 0. So imagine if the qubit is 90% 1, then 90% of the times you will measure it as 1, but 10% of the time you will measure it as 0. But I was actually looking forward to the things like quantum entanglement and things like that, which I know very little about, just only the Wikipedia stuff that's on there.
I just know Wikipedia. It's not really in depth.
Yeah, just what I read about Wikipedia. But that seems interesting, because that's about the transfer of information that goes faster than the speed of light. And that becomes really interesting, I think.
This reminds me of the riddle you had with the lamp and a wire that's it's a longer long, but goes around the lamp, and when it on its way back, its distance from the lamp is 1 meter or 50 centimeters, and then it goes another kilometer around. And then the question was, how long does it take for the lamp to light up when you introduce a current?
What would you think? Did you understand the?
not fully.
So imagine Pauline holds a lamp. I'm having a switch here. And instead of just connecting the switch directly here to there, it will run all across the world, maybe to Mars and further, and then it will go back here. So there's like a huge circuit before the electricity can reach actually the lamp. If I turn, and of course there's an energy source. If I turn on the lamp here, the switch, how long does it take for this lamp to light?
The wire is the wire goes all the way around, but it passes the lamp. Yeah.
Yeah, it just goes there to Mars, it goes back here, and of course it's short circuit.
Well,
How long will it take?
it depends on where it goes, no?
If it goes to Mars, and I have really no idea, but let's say that it takes 7 minutes lead speed of light to Mars. I really don't know, but let's assume having 7 minutes speed of light to Mars. Would it take 7 minutes, or would it rather be if you like instantly?
Probably instantly, but I don't know why. I don't know.
What you would classically think would be that the electrons, they would start moving as soon as the switch is on, so they would move, and they would move at the speed of light to Mars and back. So you would think that it would take longer, but actually it's the electromagnetic field that turns on the lamp, so it would be instantly. Even if the electrons, like, theoretically have to move to Mars and back. But that's what would interest me about the quantum entanglement and stuff like that, where you would have a piece of information now. For example, you change something here, but something is linked to it. So if you know this state, you also know the state of the other bit. But imagine they are really far apart. But by measuring this state, you will instantly also know this state as well. Even if it is like millions of light years apart, you actually know the information from light years other galaxies by measuring a state here.
And that enables the super fast information transfer.
That enables, like, that's a way of getting information faster than the speed of light, like instantly over millions of light years away. But that's really the edge of what I know about it.
And would it also help to know historical data? To calculate, I don't know, they probably calculate stuff right now about historical data.
It could be, like, if we have a good model of how information here affects something else, or how it would be entangled, then by measuring the information we see here as the electromagnetic waves or anything, the things we get in now, we might know, or we should then know, what is the state at some other so millions light years away that we cannot measure, but we know it by having the information here, because by theory it cannot be in another state than it is by measuring it now.
I feel like this is starting to lean towards time travel.
That's a kind of time travel, because you get information from somewhere to somewhere.
So it would also help with space. Well, space.
The space-time continuum.
Oh, what's that about?
Question. Michiel. I don't you tell us.
Maybe we should go one level deeper. I have a question. What's then the, very, very deep now, what's then the definition of what is life? When do you say life?
I've thought about this a lot. Yeah. Because the way we experience the world is very visual. So when I see you here, I don't actually see you. I see the light that reflects on you, and it takes time to reach my eyes. So actually, I'm already looking in the past, and I don't really see, you're not real. This is the conclusion of my thought.
You hope I'm not. Unfortunately. What would you say, like, when we search for life on other planets, what would be like the definition, or what would be the threshold that we say this is life and this isn't?
An organism that can reproduce themselves.
So, yeah, I don't know. I would say there's gradations, like emotional intelligence, up to like a central
Threshold is quite high. Do we have live or not?
sometimes, like central nervous system. And then like these, incellular, I don't know what we call it, single cell organisms, and even lower with like bacteria, something like that.
It's like a definition I learned in the IT informatics as well, because there it's also applicable.
Emotional intelligence.
It's not on the table, but where life is where you see the fight against entropy.
I like that one.
Because
I really love
nature,
that, yeah.
by definition, wants entropy everywhere, meaning that if there is like two particles here of some matter, it wants it to be as far apart to have as much entropy. And life is the fight against that entropy, because life is keeping things together and making sure there is a structure.
Yeah, especially for me, entropy was always easy to understand with thermodynamics.
Yeah,
Because
originally.
an ice cube, that's you wanting to remove a lot of heat energy.
You want the
from-
heat to be away from that specific
And
part.
all
yeah.
nature wants is for all the water in the world to be the same temperature, and for all things in the world to be the same.
For actually all matter to be the same thing. And that's,
Yeah.
so wherever there's life, there's entropy.
I like that one. Yeah. But, yeah, there's a fight against entropy.
There's a fight against
Yeah.
entropy. Yeah, correct. Yeah.
This is deep. I don't think we expected to go this deep.
Deep one. Well, we also saw a very different topic today, where we can switch to maybe, because this deep talk is very interesting, but not very connected to the logistics yet.
Not yet.
Not yet, indeed. Hopefully in the future.
It is connected to entropy.
It is.
What we'll
Logistics
discuss
is the
now.
fight against entropy. I think
Yeah.
people experience that on a daily basis,
And
definitely.
especially the Chinese shipments of Chilean cherries.
What is happening to the
Definitely
Chinese
experience
shipments
that.
of Chilean?
Of Chilean cherries.
Yeah.
Chinese shipments of Chilean. So Chinese New Year nicely coincides with the Chilean cherry season. Of course, a wonderful treat for during the holiday period. So there was one vessel carrying 1,353 reefers of Chilean cherries.
Sissies.
And it all went into shambles.
My God.
Which is an enormous amount of Chilean cherries.
And what happened?
Heel. So what happens is that Maersk Saltoro's vessel broke down, and that led to a 28-day delay, which means that the cargo of 1,553 containers of Chilean cherries arrived in very poor condition,
I heard.
which is the president of SNA warned that China might reject the cargo, pretty rightfully so, but that would trigger losses exceeding $100 million.
My God.
Exactly. And I think it's interesting to see who's gonna pay for that lost cargo. I don't know what your opinion is on this. Is it the carrier? Is it, well, the producer? Are they insured for these kind of claims? How will they go about it?
I hope it's not the growers, because usually they are the least insured, or they are the least powerful in those kind of contracts and negotiations.
They depend entirely on
Yeah, it's their life savings. Yeah.
Yeah. Apparently, the export to China is almost 90% from the Chilean cherries. Now they are expanding to India and other countries, but they are very, very dependent of China. So in the future, they should really expand to more other territories to see to not be affected in this way, because it's not good for their economy. So yeah.
What also was important here is that, of course, Chinese New Year is behind us, so they actually missed the window for where the market would actually want to buy these products. So it's predicted that this will dramatically lower the prices for cherries temporarily, as the demand has also. Yeah, it's missed its window for demand.
Very interesting insights. I don't know if there is anything else you want to talk about today.
Real-time sensor data can capture subtle variations in temperature and humidity, providing early warnings for potential quality issues.
And on that bombshell, I think we're finished.
Perfect. Thank you very much to come
Thanks so much.
today. And till next week.
Thank you. Bye-bye.